Hi there, this is your favorite math learning channel, and I have a pretty cool summation problem for you, which is involving Fibonacci sequence. So we are given A0 and A1 is equal to 1. Sometimes it's given like A1 and A2 is equal to 1. It doesn't matter. And this is the recurrence relation of the Fibonacci sequence, and we are given this thing. So we are supposed to calculate the sum. So let's start with the denominator and see if I can find a closed sum for this sum. So let's name it sk. So I will add k terms of this thing. So n will be from 0 to k. And it's just going to be a n squared. So I have all of the squares from 0 to k. And well, so now I want to get a nice representation of this a n squared. And if I can find something telescopic, it would be much better. So let's see how can I get a n squared. Well, I only have one formula. So this is my recurrence relationship. And well, you could use maybe other recurrences, but I doubt it. So how can I get a n squared? I can either just square both sides, but that would just give me many squared terms. It's not useful. Or I can just multiply all sides by a n. Let's go with the second one. So if I do that, I will just leave this a n alone. Okay, I will just keep this term on one side. So it will be a n squared equal to a n plus 1 a n. And I'm just sending this thing to the left side, so it will be minus a n minus 1. Okay, cool. And so now I need this sum from 0 to k. I can just add all sides. N is from 0 to k. So here there's a little problem on the right side. I have that n is equal to 0, but this would just give me a of minus 1. And I don't know if it's defined actually. You can actually say that, so since it's going like 1, 1, 2, it can also be defined for negative numbers, and you can say this term is 0. But this is a little sketchy, so let's not do that. And I can actually get rid of this thing by saying I can just take these sums from n is equal to 1. And then I can just add one more term. So if I do that, I will just rewrite this sum. So the first one is same. I'm separating the sums. a n plus 1 a n. And for this one, so this is also from 1 to k. I can just put n is equal to n plus 1 so that it will look exactly like this. a n plus 1 a n. And so since I increased it by 1, the index will shift 1 to the left side. So it will be just from 0 to k minus 1. So like I said, these two are just exactly the same. I'm adding from 1 to k and 0 to k minus 1. So the like intersection will just simplify. So from 1 to k minus 1, they will just simplify and make 0. And I will only be left with the last term of this thing, which is ak plus 1. AK. And from this one, I will have the 0th one, which is A1 times A0 minus. And A0 and A1, they're both 1, so I can just put 1. Okay, cool. And so, like I said, we calculated it from n is equal to 1 to k, but we actually need it from 0. So I can just add the A0 term on both sides. So basically, I had this thing. N is from 1 to k. a n squared. And so now I can just add a0 term, a0 squared on both sides. So on this side, I will just get this thing, what I needed. It's from 0 to k, a n squared. Or now I will use just different indices because I want to show it like a n in the end. It would be just nicer for me. And I can put k here, or I, it doesn't matter. So I just have this thing, ak squared. This is going to be equal to n. Instead of n, I will just put n, a n plus 1, a n. So I have minus 1, and a0 squared is just going to be 1. a0 is 1, so it's plus 1. So these two will just cancel. I will delete it. So this is equal to Sn. I said Sk, but now it's Sn. So this is our denominator. We found a nice, simple closed form for this denominator. So let's just make an arrow here and say this is equal to, I will not put equal, so this thing is just an plus 1 an. Pretty simple. And for the top part, so this was basically half of the question. And the other part, well, this is actually not easy. Like, we could just solve this from scratch, but it's not easy to just represent this from scratch. There is a relationship between -1 to the n and Fibonacci sequence, and this is called Cassini's identity, which just says that an minus 2 minus an minus 1 squared is equal to -1 to the n. Like I said, like, if you don't know it, you can just deduce it easily. I will prove this. Well, you can prove it by induction or just using what is general term of the Fibonacci sequence an. I also made a video about it. And or one way is more clever, but again, like, it's even harder to see. I will solve it with that way. So we can define a matrix A, which is 0, 1, 1, 1. It's defined like this so that I want to take powers, and I will see that if it's including Fibonacci numbers, and matrix multiplication is like a natural way to do it. So I have A, I define it like this, and if I look at A squared, so it's just 0, 1, 1, 1 times 0, 1, 1, 1. This is gonna be, so this row times this column, it will be 0 times 0, 1 times 1, it's just 1. This is gonna be 1, this is gonna be 1 again, and this is 1 plus 1, which is 2. And A cubed is gonna be just this thing, 0, 1, 1, 1, 1, 1, 1, 2. So this is gonna be 0 times 1, so, and 1 times 1 is 1, and from this I will get again, so this will be 2, this will also be 2, and this will be 1 plus 2, which is 3. And if you did again, I will just write the answer for this one. You can just keep doing this. It will be 2, 3, 3, 4. So basically, if you look, like, I had 2 at the second one, it came on the first, and I had this last one, it came at the diagonal, and I got actually the sorry, this should be 5, and I got the next Fibonacci number. So let's write, like, terms of the Fibonacci sequence, and then we will see what's going on. So I have an and n. So we defined it from 0, 1, 2, 3, 4, 5. And an was 1, 1. So then it's just 2, 3, 5, 8. It goes like this. So let's start from just the a4 term and try to find, like, what would a to the n look like. So, for example, this term is 2. And what is 2? So the value is 2. And if I look here, this is 2. So it's a2. So this thing is a2 when n is 4. So we can guess it's probably a of n minus 2. And for example, this one is 3. This diagonal is 3. And I can say that the value 3 is belong to a3. So this is just one less, an minus 1. This one is same. And the last one, so this is 5. And if I look at 5, the value 5, it's a4. And so this is a4. It's just exactly the same. I have power of 4, and this is a4. So this is just going to be an. You can, here, like, I won't use induction to show this. You normally are supposed to, but it's just one step, and you will just multiply this thing by 0, 1, 1, 1, and you will get it. It's really easy. And now, so why did I do this? Now, if you look at this thing, determinant, which is this times this minus this times this, it's exactly equal to this left side. So if I do that, the determinant of this thing is gonna be equal to, let's call my left side a, okay? So this is equal to a, and also, so there's a property of matrix determinant, and so if you have if you're multiplying two stuff, you can separate them. Okay, this is really important property of determinant. And so you can just take b is equal to a, and with this way you can just multiply all of the n's, and therefore you can actually, another way to show this is that so this is just a to the n. And now it's really easy to just calculate determinant of a, because it's just 0 times 1 minus 1 times 1, which is just minus 1. So this is indeed minus 1 to the n. So I showed that my left side a is equal to minus 1 to the n, and so this proves this identity. Okay, so what did I say? This thing is just equal to this thing. Let's write it: an minus 2 minus an minus 1 squared. Okay, cool. So now I want to just put them here and calculate the sum. But there is a little problem. So my sum is n starting from 0, but if I put 0, I will just get like a of minus 2, and it's also not cool because I don't know if it's defined there. So instead I can use a similar trick, and I can just first open one term. Okay, so first of all, let's say my answer is s, and now, so I will say that, for example, my sum s converts from, let's say, bn. So basically bn, or let's say bk, is my sum that n is from 0 to k. So this is exactly my sum. Let's write it: an minus 2, but I can't write it like this here for this step. Let's just write it like this: minus 1 to the n over, and this thing was true for any n, so I can just write this thing: an plus 1 an. So like I said, I want to take the first term out. So if I do that, it will be n. If n is equal to 0, it's gonna be 1 at the top, and a1 times a0 is also 1, so it will just be 1. And plus, it will be n is from 1 to k minus 1 to the n over just an plus 1a. Now it's a bit nicer, but I still can't put n is equal to I can still put n is equal to 1 here. So what can I do is, like, I can, instead of having this thing here, so this is equal to minus 1 to the n, if I put so I will just delete this, I will make changes here. If I put n is equal to n plus 1 here, I will actually get something simpler. So instead of n, I will put n plus 1, so it will be a of n plus 1, and this was n minus 2, so it will be just n minus 1, and this is gonna be just an, and this will be n plus 1. Let's write it nicer. So I could just write it like this too. This is true for any n greater or equal than 0. But now here I have minus 1 to the n. So what can I do is that I can just make this minus and make this thing n plus 1. And now I can just substitute this thing here. So I will take this thing and put it here. So what will it look like? Let's make it a bit bigger. So it will be, I actually made it bigger by mistake, but it's useful. So it will be n is from 1 to k. And so I have this thing, which is an plus 1, an minus 1, an plus 1, an minus 1, minus an squared over, and it's just an plus 1a. Okay, cool. Now I will try to do it on purpose. Okay, cool. So let's delete this. I put it there. Now it's pretty simple. So I have 1 minus, and it will be, so I can just divide it and separate the sums. So it will be am plus 1s will just cancel out for the first part, and it will be am minus 1 over an. And from the second part, I will get an over am plus 1 minus, let's separate it, an over am plus 1. And my sum is just from 1 to k. N is from 1 to k. Okay, cool. And if you look here, this is also like telescoping. If you put n is equal to n plus 1 here, this is just exactly this equal to this thing. So what can I do is that I can just say 1 minus, or I will just change it on this step again. I'm lazy. So I can put n is equal to n plus 1. So it will be from 0 to k minus 1. And I'm putting n is equal to n plus 1. So this will be just an. And this will be n plus 1. Cool. So again, I'm adding from 0 to k minus 1, 1 to k. So the common ones will just cancel, which is from 1 to k minus 1. And I will be left with only these terms. So this will be just 1 minus the 0 term of this, which is a0 over a0 plus 1. And also here, I had, so this thing was in parentheses. This thing should have been in parentheses. I didn't put parentheses. So this should be actually a plus. And so if I put k here, it will be plus ak over ak plus 1. So now what's up? I found my partial sums, bk, is equal to, and I can just write this thing. So this is just 1 over 2. I can just say it's just 1 minus 1 over 2 plus this thing. So it's just 1 over 2 plus ak over ak plus 1. And so this is equal to bk. Let's put it here. 1 over 2 plus bk. Wait, is it actually bk? No, ak. Doesn't make sense. Ak over ak plus 1. Okay, cool. So now I want to take this limit as k goes to infinity, then it will be equal to my sum. But it's not that easy, because now I need to have this limit as k goes to infinity. This is actually a really like pretty popular property of Fibonacci sequence. If you know that, like for example, it goes like 1 1 2 3 5 8, so it just goes like this. And if you get bigger, for example, I don't know, like let's just I will just make it up. For example, 1 is like 1 0 0 1, and the next term will almost be approximately like 5 times of this. I will just multiply this by golden ratio, which is 1 plus square root of 5 over 2, and I will get the next term. So if it's like, especially if they're big, this thing will just be true. Okay, and this is how I show a big number with 1 0 0. So actually, well, I will also show this just for you, but first I will just take this limit, and then I will show that this limit is equal to, so this thing is just less than that, so this will be just 1 over 5. So if I do this, this thing will just converge to bk, will just converge to as k goes to infinity. 1 over 2 is just a number, so it's 1 over 2. And this thing, like I said, so it will just converge to 1 over 5, because ak plus 1 over ak converges to 5, and 5 is just 1 plus square root of 5 over 2. So I can just flip it. It will be 2 1 plus square root of 5. And this is actually my answer. So I will stop the video if I make a mistake at the calculation of this limit. So this is our answer. This is equal to S, equals to capital S. And now, so I want to show that this holds how do I show it? Well, I need to have the general term of the Fibonacci sequence. Previously, I made a video that's showing this. It was 1 over square root of 5. So I have phi to the n, and plus, let's use another letter, mu to the n. So it was this thing. And I know that phi is just 1 plus square root of 5 over 2. And this is 1 minus square root of 5 over 2. So this is, these are the roots of the polynomial x squared minus x minus 1. And I proved this thing, okay? So these are the roots of this polynomial. And actually, in that video, it was a1 and a2, it was equal to 1. So I should actually say these are minus 1. Or I can just say a of m plus 1 is equal to this thing. And so similarly, I can just write an. It's just going to be 1 over square root of 5. So it will just be phi to the n minus 1 plus mu to the n minus 1. And so basically, I want this limit an over an plus 1. So I will just take this ratio an over an plus 1. This is going to be equal to, so 1 over square root of 5 will just cancel. And I will be left with phi to the n minus 1 plus mu to the n minus 1 over phi to the n plus mu to the n. Okay. Here I can just take phi parentheses for all sides, because here it's actually is a limit because mu is just less than 1. If you look at this thing, it's just this thing is just less than 1. So I can just take both sides, phi to the n minus 1 parentheses, and I will okay, it will be 1 plus mu over phi to the n minus to the n minus 1 over, and I can take this part into phi to the n parentheses. This will be 1 plus, so this is just mu over phi to the n minus 1. Okay, so here the only thing I can notice is that this thing, if I look at this thing, this is like of course this thing is just less than this thing, okay? So this is bigger than that. And if I take ratio of this and take it in absolute value, 1 minus square root of 5 over 2, which is mu, over phi, I will, okay, let's write it like this, square root of 5 over 2. This is of course less than 1, because their absolute values are just smaller, because this thing just has plus, this thing has minus. Of course this thing is smaller in absolute value. So therefore I can just say this thing, this parenthesis, its absolute value is less than 1. Okay, so this is less than 1, but not itself, but well, it's also true for itself because it's negative, but we can say its absolute value. And I know that if I take limit of this thing, this stuff will just go to 0, because it's between minus 1 and 1. Something is between minus 1 and 1. And then if I take it, its n power, a to the n will just converge to 0. So this thing will just go to 0. And also this is just n. It doesn't matter. So this will also go to 0. So this goes to 0. This goes to 0. That's a lot of arrows. So this thing will just go to, so these two will just cancel. 1 over phi. And it will just be 1 plus 0 over 1 plus 0. It doesn't, it's not useful. So this is just gonna converge to 1 over phi. And so this shows that this property, well, it's really like popular in, like also in popular math. It's really well known. People believe that Fibonacci sequence and golden ratio is like holy in mathematics, and it's really important, but it's not. And most of this stuff are lies. So they tell like, oh, there's a spiral and oh, it's everywhere. No, it's not. Okay, so this is a nice way to finish the video.